10:45 in the morning on February 3, 2026, a missile-shaped test vehicle left the integrated test range at Chandipur. A ground booster drove it to the speed an air-launched weapon would already possess. Then a nozzle-less booster, a solid fuel ducted ramjet motor, and a fuel flow controller performed as expected. That is what India's Ministry of Defense officially confirmed. Online, the event was quickly described as a test of Astra Mk3, also called Gandiva, a future very long-range air-to-air missile. But those are not identical claims. A propulsion demonstrator can prove that an engine breathes, burns, and responds in flight. It does not by itself prove a complete combat weapon. This film follows the evidence from that launch into the engine, through the equations, and back into the sky. The central question is simple. What does SFDR change, and what must Gandiva still prove? First, the name. Indian reporting widely uses Gandiva for Astra Mk3, borrowing the name of Arjuna's bow from the Mahabharata. DRDO's own newspaper clipping service has reproduced that reporting. Yet a clipping collected by an agency is not the same thing as a program specification signed by that agency. In the official releases examined for this film, the government describes SFDR technology and its purpose, enabling long-range air-to-air missiles. Does not publish a Gandiva configuration sheet, a certified maximum range, a seeker type, an induction date, or an operational squadron. So the film uses Astra Mk3 and Gandiva as reported program names, while treating the demonstrated hardware as SFDR technology. That distinction is not pedantry. It prevents a successful engine experiment from becoming, through repetition, a fielded missile with imaginary specifications. Evidence first, interpretation second, prediction last. The known baseline is Astra Mk1. India's Department of Defense production lists it as an indigenous beyond visual range air-to-air weapon manufactured by Burret Dynamics and designed by DRDO. The public product page gives a range of 80 to 110 kilometers, a solid rocket motor, inertial guidance with mid-course updates, and terminal active radar homing. In 2022, the Ministry of Defense signed a contract for Astra Mk1 missiles and associated equipment for the Air Force and Navy. Those facts matter because Gandiva is not appearing from nowhere. It grows from an ecosystem that already knows how to separate safely from an aircraft, navigate toward a moving target, receive updated information, activate a seeker, and manufacture an air-to-air weapon. But the propulsion leap is profound. Astra Mk1 carries both fuel and oxidizer inside a rocket motor. SFDR tries to leave much of the oxidizer outside the missile, in the atmosphere. Beyond visual range is not one fixed distance. Imagine two fighters closing head-on at high altitude. The launch aircraft is fast, the air is thin, and the target is flying into the missile's path. Now reverse the geometry. The shooter is low, the target is fleeing, and the missile must climb through dense air while chasing something already moving away. The same weapon can produce radically different reach. A brochure's maximum range is therefore a boundary condition, not a universal firing distance. What crews need is an engagement envelope. Launch altitude, launch speed, target aspect, target maneuver, atmospheric density, guidance updates, and the energy remaining at intercept. A missile that arrives far away but too slowly to turn with the target has achieved distance, not necessarily a kill. SFDR is valuable because it attacks this energy problem, especially late in flight. Conventional solid rocket is brutally effective. Ignite it and chamber pressure accelerates hot gas through a nozzle, producing thrust. There's no air inlet, compressor, turbine, or liquid fuel pump. But the missile must carry fuel and oxidizer together, and the motor's energetic burn is usually concentrated early. After burnout, the weapon coasts. Drag keeps taking energy away while turns consume even more. Designers can use dual-pulse motors to divide the burn, saving a second impulse for later, but the oxidizer still occupies volume and mass. An air-breathing ducted rocket changes the bookkeeping. Once it is fast enough, it captures atmospheric oxygen for the main combustion process. That can support sustained thrust through more of the engagement. The advantage is not magical speed. It is the ability to manage energy over time, so the missile may reach the terminal fight with more authority. Ramjet has no rotating compressor. Forward speed does the compression. Supersonic air meets the inlet in a controlled system of shock waves. The diffuser slows that flow and raises its static pressure and temperature. In a conventional ramjet combustor, the flow is brought below the local speed of sound so fuel can mix and burn stably. Heat addition raises the gas energy. A converging-diverging nozzle then accelerates the exhaust rearward. Thrust balance can be written compactly. Mass flow multiplied by exit velocity minus mass flow multiplied by inlet velocity, plus the pressure difference across the nozzle exit area. More air captured and more useful exhaust velocity can mean more thrust, but every shock and every patch of friction costs total pressure. The inlet must therefore be both an air collector and a precision shock machine. Too little compression and combustion weakens. Too much back pressure can destabilize the inlet. Engine cannot begin from rest. A ramjet needs sufficient forward speed to compress its incoming air, so SFDR uses a sequence. In ground tests, an initial booster simulates the energy an aircraft launch would provide and accelerates the vehicle. The 2019 release says the demonstrator was guided to altitude to simulate aircraft release conditions. A nozzle-less booster then pushed it to ramjet operating speed. Nozzle-less does not mean no exhaust path. It means the booster grain can burn through a shared flow passage that later becomes part of the air-breathing duct, avoiding a conventional nozzle that would obstruct the ramjet. When the booster phase ends, inlet air enters the duct and the sustainer takes over. The transition is a difficult instant. Geometry, pressure, ignition, separation, and control must all agree while the vehicle is already traveling at supersonic speed. The phrase solid fuel ducted ramjet sounds contradictory. Ordinary solid propellant is difficult to stop or throttle once lit. The solution is to separate fuel generation from final combustion. A gas generator burns an oxygen-poor, fuel-rich solid grain. Instead of producing the final jet by itself, it creates hot, combustible gases and particles. Controllable throat meters that fuel-rich stream into the main ram combustor, where oxygen from the captured air completes the reaction. DRDO researchers have published controller work for this architecture. Their objective is not simply to open a valve. Gas generator pressure, throat area, airflow, demanded thrust, time delay, and safe operating limits form a coupled nonlinear system. The controller must deliver enough fuel for commanded thrust without driving the combustor or inlet into an unstable condition. That small mechanism is the difference between merely sustaining and intelligently managing propulsion. In February 2026, the fuel flow controller was one of the subsystems officially reported to have performed as expected. Why is that important? Consider 3 phases of an intercept. Early in flight, high thrust can build speed and climb. During cruise, a lower flow rate can conserve the finite solid grain. Near the target, greater thrust may restore energy for a hard turn. The exact schedule is not public, and real control authority is constrained. SFDR is not an infinitely adjustable jet engine, but modulation changes the design problem from one irreversible burn toward a managed energy budget. The control loop compares a command with measured or estimated engine behavior, moves the metering mechanism, and watches pressure respond after a delay. If it chases the error too aggressively, it can oscillate. If it responds too slowly, the missile may miss the energy state demanded by guidance. Propulsion and guidance become partners. This leads to the most useful operational concept, the no-escape zone. Maximum aerodynamic range asks how far a missile can travel under favorable assumptions. The no-escape zone asks whether a target can turn away, accelerate, descend, and still be caught. It is always smaller, and it changes with geometry. Sustained propulsion can enlarge it by reducing the penalty of a long coast. If the target turns cold, the missile continues receiving thrust instead of relying only on stored velocity. If guidance commands a late maneuver, the motor may help replace energy lost to induced drag. That is why ramjet weapons are often discussed in terms of terminal energy rather than headline distance. But no public source examined here gives Gandiva's verified no-escape zone. Any precise colored bubble would be invented. The honest visual is conditional, bigger or smaller depending on altitude, aspect, speed, updates, and target behavior. Propulsion cannot find a target. A long-range engagement is a chain. The launch aircraft or another sensor builds a track. The missile leaves on an inertial solution. During mid-course flight, updated target information can reduce the error caused by maneuver. Near the intercept, an onboard seeker must acquire and track in an electronic environment shaped by clutter, jamming, decoys, and geometry. The official Astra Mk1 description confirms inertial guidance, mid-course update, and terminal active radar homing for that weapon. It is reasonable to expect any future very long-range Astra require an equally demanding chain, but the precise Gandiva seeker and network architecture remain outside the official evidence reviewed here. More range increases the need for good updates because prediction error has more time to grow. A powerful motor sent towards stale coordinates is not a long-range capability. It is merely a fast vehicle flying to the wrong place. Altitude helps and hurts an air-breathing missile. High up, lower density reduces drag, so velocity is cheaper to preserve. A fast, high launch also contributes kinetic and potential energy before the missile motor does any work. But a ramjet needs oxygen mass flow. Capture area, air density, and flight velocity determine how much air enters the engine. Thin air can therefore reduce available thrust even as it reduces drag. Designers balance inlet geometry, fuel flow, trajectory, and angle of attack across this changing atmosphere. Public reports often assign Gandiva a maximum reach around 300 to 350 kilometers, sometimes with different figures at different launch altitudes. This film does not treat those numbers as certified performance because a primary specification has not been published. Their direction is physically plausible. High and fast launches favor range. Their precision is not independently verifiable. The atmosphere, not a single number, sets the real envelope. Public test record shows accumulation, not one sudden breakthrough. In May 2018, DRDO reported a technology demonstrator flight, and India's first successful demonstration of the nozzle-less booster in that mission. In February 2019, A second indigenous SFDR system demonstrated ground booster operation, separation, simulated air release conditions, nozzle-less boost, and acceleration to ramjet Mach number. March 2021, another flight proved subsystems and new technologies while range instruments watched from Chandipur. April 2022 added a flight test described as validating the reliable function of critical components. The ministry's 2023 year-end review said an SFDR-powered air-launched tactical missile had been flight tested with a nozzle-less booster, thrust modulation, and a sustainer delivering specific impulse in ramjet mode. Then came February 2026, motor, booster, and fuel flow controller again performing as expected. Each test closes risks. None alone certifies the entire weapon. Launch photographs show one vehicle. The program is a distributed machine. Official releases identify the Defense Research and Development Laboratory, Research Center Amarat, High Energy Materials Research Laboratory, the Integrated Test Range, the Indian Air Force Industry and Instrument Teams. Their tasks span propulsion, energetic materials, guidance and control, telemetry, tracking, airframe integration, manufacturing, and trials. Astra Mk1 already connects DRDO design with Burret Dynamics production and aircraft integration. An SFDR weapon adds demanding inlet surfaces, hot fuel-rich flow, a metering actuator, thermal protection, and tight dimensional control. A motor that works once is science. A motor built repeatedly, stored safely, carried under vibration, released across an aircraft envelope, and maintained by squadrons is a weapon system. The industrial challenge is therefore statistical. Can every unit behave within tolerance after transport, aging, heat, cold, humidity, and years in storage? Future missile also has to become part of an aircraft. The pylon must carry its mass and aerodynamic loads. The weapon must separate cleanly at different speeds, altitudes, and angles. Power, cooling, and digital messages must pass through the interface. Mission computer software must understand launch zones, failure states, and target updates. Radar and electronic support sensors must provide tracks good enough to exploit the range. Astra Mk1 is publicly associated with the Su-30 MKI, and DRDO demonstrated its firing from Tejas in 2023. Those images establish an Astra integration pathway. They do not show Gandiva. Reports speculate about future carriage on several Indian fighters, but a platform list is not official merely because it is technically desirable. The size of an SFDR missile, inlet clearance, launcher compatibility, and flight test program will decide where it can actually go. Integration is where an impressive cylinder becomes a usable combat capability. The closest public conceptual comparison is Europe's Meteor, whose manufacturer describes a throttleable ducted rocket motor and emphasizes sustained propulsion and a large no-escape zone. That makes Meteor useful for explaining the class, not for assigning Gandiva equal performance. Airframe size, propellant chemistry, inlet recovery, thrust schedule, seeker, data link, launch aircraft, and test maturity all matter. Public discussion also compares Gandiva with long-range rocket-powered weapons, but raw maximum range figures conceal different assumptions and missions. Some weapons may be optimized to threaten large support aircraft. Others may prioritize fighters, electronic warfare resistance, compact carriage, or terminal agility. Without matched launch conditions and verified envelopes, a ranking table creates false precision. The defensible conclusion is narrower. India has repeatedly demonstrated the critical propulsion architecture required for a sustained thrust, long-range air-to-air missile. Whether the complete weapon matches any named foreign system remains unproven in the public record. Between a propulsion demonstration and operational service lie gates the public record has not yet closed. An aircraft must carry and safely release the full configuration. The inlet must start across altitude, speed, and angle of attack limits. Propulsion must transition reliably and follow commanded thrust. Guidance must receive updates during long flyout. The seeker must acquire representative targets in clutter and electronic countermeasures. Fuse and warhead must complete the end game. Tests must cover head-on, crossing, and receding geometries, maneuvering targets, maximum and minimum ranges, hot and cold conditions, captive carriage, vibration, storage life, and production consistency. User trials then ask whether aircrew and maintainers can employ the system repeatedly. Official SFDR success is a major enabling result. It is not evidence that all these gates are complete. Development deserves credit precisely because the remaining work is difficult, measurable, and real. Turn to Chandipur. The 2026 vehicle was accelerated to the required Mach number. Its nozzle-less booster, SFDR motor, and fuel flow controller behaved as expected, and multiple tracking instruments recorded the flight. That is a meaningful demonstration of a hard technology, a compact air-breathing propulsion system that can generate and meter fuel from a solid grain, while a supersonic inlet supplies oxygen. The physics explains the promise. Carry less onboard oxidizer, sustain thrust, manage energy, arrive at the terminal intercept with more capacity to chase a maneuvering target. The evidence also defines the limit. Publicly reported names and range figures do not substitute for full weapon trials, verified envelopes, aircraft integration, production, and induction. Gandiva may become the long arm of India's Astra family. Today, the most defensible story is more interesting than a superlative. India has taught a missile engine to breathe, and is still teaching the complete weapon how to fight.